let's talk about something that drives every single one of us crazy: debugging a machine learning training job. Today, we're going to put on our detective hats and turn that frustrating process into a bit of a mystery we can actually solve.
Oh man, we have all seen this, right? You've got your code, you're excited, you hit run, and you're greeted with this monster. A wall of text that basically means something's wrong. This is where our investigation begins, the case of the failing training job.
And that's when the panic sets in. You know, that sinking feeling where you're just lost. The error could be anywhere. Is it my data, my model, my optimizer? It's so easy to get overwhelmed. But here's the thing. A good detective never panics. They have a system. So let's lay out the crime scene. The problem with an error inside model.fit is that it's the grand finale, where everything comes together. Your data, your model, your loss function. It's like trying to figure out why a cake tastes bad after you've already baked it. The problem could have happened at any step. So, instead of just randomly changing things and hoping for the best, we've all done it, we need a game plan. We're going to approach this methodically. We'll start at the very beginning of the pipeline and check each component one by one. That's how we'll find our clues. To do that, we need a simple, repeatable process. This is going to be our detective's toolkit. It's a mental model that will help us bring some order to all this chaos, and honestly, you can use it to solve pretty much any training mystery. And here it is. It's that simple. 3 steps. Is my data okay? Is my model set up correctly? And finally, are my hyperparameters making sense? This is the roadmap for our whole investigation. So let's start with number 1, the data. Okay, case file is open. We're going to tackle that first scary error message we saw by using our new framework. And we're starting with the prime suspect in almost every ML mystery, the data itself. So, clue number 1 is the missing gradient. What does no gradients provided actually mean? Well, in plain English, it means your model isn't learning at all. The feedback loop is broken, and our framework tells us the first place to look isn't some complex part of the model, but simply the data we're trying to feed it. And boom, here's our culprit. See what was happening on the left? We were putting the labels inside the input dictionary, but we were telling Keras to use an external loss function that was expecting the labels to be passed in separately. It couldn't find them. The fix, on the right, is just to tell the model, hey, calculate the loss yourself, because the model knows to look inside that dictionary for the labels. Simple. So we fix the code, we hit run, we're feeling like a genius. The gradient error is gone. Progress. But just when we think the case is closed, a new clue emerges. And this one is a lot sneakier. Nan, not a number. This is probably the most infamous villain in all of machine learning. It's this silent killer that pops up when a calculation goes wrong, like dividing by 0, and it has the nasty habit of destroying everything it touches. You gotta think of nans like a poison. As soon as one appears, it spreads like wildfire. Anything you multiply by nan becomes nan. Pretty soon, all your model's weights are corrupted. The key is to find patient 0. So we'll reset the model and look at the output of just one batch before any training happens to see exactly where that first nan shows up. And there it is, the smoking gun. We took a fresh model, ran one batch through it, and looked at the loss for every single example. And do you see the pattern? The loss is only nan whenever the label is 2. That is not a coincidence. That is a massive clue. Here's the reason why. The model was configured with num labels set to 2, which means it was only expecting to see labels 0 and 1. When it saw a label of 2, it had no idea what to do, panicked, and produced a nan. By simply changing that to num labels equals 3, we solve the mystery. 2 down, 1 to go. Okay, deep breath. The model is training, no errors, no nans, we're good. But wait a minute. The loss isn't going down. It's just kind of bouncing around. This is our third and final clue, stalled progress. The data's fine, the model is set up right, so our detective framework points us to the last suspect, the hyperparameters. And just look at the difference here. We were using the default learning rate for the atom optimizer, 0.001. But for these big transformer models, the recommended rate is way, way smaller, like 5e to the -5th. That's 20 times smaller. Our learning rate was so high, the model was just jumping all over the place, completely overshooting the right answer every single time. It couldn't make any progress. All right, we solved our main case. Now for the speed round. let's fill up our debugger's handbook with a few more tips and tricks from other common cases. These are things you'll want to have in your back pocket. First up, the classic out-of-memory error. If you ever see OOM, your first move, 99% of the time, should be to just cut your batch size in half. It's a simple fix that often works. Oh, and a little tip for TensorFlow users. It likes to grab all the GPU memory it can see, so make sure you don't have another notebook running in the background stealing your resources. Now, this next one, honestly, this might be the most powerful sanity check in all of machine learning. Before you try to train on your entire massive dataset, just take one single tiny batch of data, and then try to train your model on just that one batch over and over again. If your model can't even learn to memorize one tiny piece of data, if it can't get the loss close to zero, then something is seriously broken with your setup.
And please remember this. It will save you so much grief. Do not start fiddling with hyperparameters until you know your model can actually learn something. It's so tempting to start tweaking things, but you're just making the mystery harder to solve. Your motto should be, get it working first, then make it great. So we've followed the clues, we've solved the case, we've added some new tools to our handbook. Let's just take a step back and think about the big idea here, about what it really means to become a master ML detective.
And this is really the heart of it. The point of all this wasn't just to fix those 3 specific bugs. It was to learn a process, a systematic, repeatable framework, check the data, check the model, check the hyperparameters that you can use to tackle any problem. It's about having a plan so you never feel lost again. So now you have the toolkit. You're the detective. The next time you see one of those awful error messages, you'll know exactly where to start looking. Thanks for joining the investigation.